It's my pleasure to welcome you to the GMAT 41's General Physics class. In this class, we shall look at the topic linear momentum and collision. Linear momentum and collision. When an object is in motion, if a body is in motion, the body has mass and it's moving with, say, velocity. Alright, one can define the momentum of that body. In most cases, you hear someone say, I have momentum, you know. So what is this momentum? It is simply the product of mass and the velocity of an object. So if the object is moving, it has velocity. Simply multiply the mass of that object by its velocity, you get the momentum of that object. We have this equation here that momentum is equal to mv. Is that okay? Now, when this object is moving, there is every possibility that the object may collide with another object. Alright? There might be this impact. And when there is this collision, it's possible for the momentum of this object to change. If, for example, the object is moving with a momentum of, say, 20 kilogram meter per second initially, after colliding, the value may change. The value may increase or decrease, as the case might be. It therefore means that it becomes important for us to define the initial and final momentum of an object. Is that okay? And here on the board we have it. If we take the initial velocity of the object to be u, so in our study of linear momentum here, we are taking the initial momentum, or the initial velocity to be u, and of course, the final velocity we take it as v. Now for that particular object, it has mass m. If you do mass times u, you would get the initial momentum of the object. And then if we do mass times v, we would get the final momentum of the object. Now, this brings to our mind the need to find the change in the momentum of this object. Since we have initial and final, of course we expect that the change in momentum is going to be final momentum minus what? Initial momentum. You know, change in momentum will be equal to mv minus mu. And that means that the mass being common can be factorized, and then you have the change in momentum to this. That's how we got this equation 2. So you take note of this. Momentum is product of mass and velocity. But the change in momentum is final momentum minus initial momentum. In the next video, we are going to consider the concept of impulse, of course, as a result of impact. In the previous video, it was stated that when an object is in motion possessing momentum, it's possible for this object to collide, right? To collide with another object. Now, this collision is an impact. That brings in the concept of impulse. Now, when there is a collision and impact, you know, two objects comes together, they hit with a certain force. Is that not so? Now, there is a time interval during which that force acts. Does that make sense? When two objects collide, that is impact, bringing in the concept of impulse. During the collision, the force with which these objects collide usually occurs within a certain time interval. That defines impulse for us. Impulse is the product of the average force and the time during which the force acts on a particle. So if this object moves and then this object approaches this one with a force, alright? So the time during which this force acts on this object, the product of that force and the time is what we refer to as what? Impulse. Mathematically, impulse is equal to Ft. Actually, it's meant to be F times change in t. But if we take the initial time to be 0, and then the final time to be t minus 0, that change will give you t. So we'll simply define it as this equation 1 here. I equal to Ft. I is the impulse, F is the average force, and t is the time during which that force acts on the particle. Now, this takes us to this theorem known as the impulse momentum theory. You see, momentum is responsible for impulse. Because if there must be an impact, an object must have to possess a momentum before it can collide with another. So there is this relationship between impulse and momentum. It's given by this theorem here, the impulse momentum theory. This theorem states that the impulse that is applied to a system changes the momentum of that system. When you apply impulse on a system, the momentum of that system is expected to change. Now, the change in momentum there is exactly equal to the impulse applied. That is the impulse momentum theory. And this makes sense. You know, when an object is moving like this, it moves freely with mass times velocity going on its own. But of course, when it collides, there's an impact. Now, this impact, like I said, bringing the concept of impulse, it changes the particle's momentum. And so the impulse momentum theory is now telling us that a change in that momentum is exactly equal to the impulse. Now, how can we prove this statement? It's an easy one. From base definition, impulse is force times time. But we know that force is mass times acceleration. Is that not so? So if we fix in mass times acceleration here, we'll get impulse to be equal to mass. And not the mass we lie down on. Is that okay? And not the one we use for floor covering. That's mass times acceleration times the time of impulse. Now, acceleration we learn from linear motion. As motion along a straight path to be equal to change in velocity divided by time. Remember that, right? So acceleration is final velocity minus initial velocity divided by time. We encountered that already. So if we actually substitute that here, you would notice that we'll have impulse equal to mass times v minus u over t times this t. And this time will eventually cancel out. I'm cancelling out to have impulse to be equal to mass times change in velocity, that is final minus initial. And of course, we remember that in the previous video when we established the formula for a change in momentum, we got it to be mass times change in velocity. Is that not so? Therefore, proving the fact that impulse applied to a system changes the system's momentum, and the impulse is exactly equal to what? The change in momentum. In the next video, we are going to look at the application of Newton's second law, alright, to the study of linear momentum. And of course, we're going to look at his third law, action and reaction being equal and opposite, as we consider the law of conservation of linear momentum. In this video, we are going to look at the law of conservation of linear momentum. Alright? When we have systems of objects interacting, colliding, there is a law that guides the momentum. That law is the law of conservation of linear momentum. Please, it's very important for us to know that for this law to hold, there are two requirements, two criteria that must be met. And these are the criteria. One of them is that the mass of the object must remain constant during the collision. During the interaction, these objects colliding, are you following, right? These objects that are interacting, their masses should be constant. That is, if before and after collision, there should be no change in their mass. And then secondly, the total or net external force on the system is expected to be zero. What does that mean? It means that there should be no external force acting on these objects that are colliding. Once these two conditions are satisfied, then the law of conservation of linear momentum holds. Can we now state the law? The law of conservation of linear momentum states that in any system of colliding objects, the total momentum of the system remains the same, is constant, does not change. Is that okay? Total momentum is always conserved on the condition that there is no net external force acting on the system. Of course, that's why we talked about these two conditions being satisfied. So that is the law of conservation of linear momentum for us. On the basis of the fact that these two conditions should hold for momentum to be conserved, we can then write the equation in this form, that the summation of all the momentum of the object, I used I there, where I could be 1, 2, 3, 4, depending on the number of objects you have. But generally, we are going to restrict our discussion to the collision or system of two objects. Is that okay? Now, if you sum all the momentums, it should be equal to what? A constant. And of course, for something to be equal to a constant, it means that the initial value of that quantity will be equal to the final value of that quantity. Take note of that, because in the next video, we're going to establish the law of conservation of linear momentum mathematically in terms of two objects that are interacting, that are colliding. Please note, if these two conditions are met, a system that meets these two conditions, is known as an isolated system, and an isolated system is also closed. So such system is known as an isolated and closed system. In the next video, we shall now establish the conservation of linear momentum theory as a law that is obtained or dependent on Newton's third law of motion, that action and reaction are opposite and equal. In this video, let us now apply the law of conservation of linear momentum to obtain an equation for the conservation of linear momentum. So we consider this system here. This is object A and object B. They have their masses. So we're going to refer to their masses as mass A and mass B. So MA and then MB. Now we see that initially these two masses are moving in the same direction. Remember that momentum is a vector quantity, so direction matters. Therefore, if we assume that these two objects are moving in the same direction initially, then it means both of them, their momentum will take the same sign, which we're going to give them to be what? Positive. Because they are moving in the same what? Direction. Now, after colliding, they will have final momentum. According to the law of conservation of linear momentum, remember that the sum of initial momentum is equal to the sum of final momentum. That is the same as saying that the total momentum is constant. Is that okay? Now, on the basis of that, we have this equation here on the board. So summing the momentums initially, so we're going to have mass of A times initial velocity of A plus mass of object B times initial velocity of object B. Is that okay? So these two terms will be added. Positive, positive, because these two masses are moving in the same direction. And then after collision, that is now going to give us mass A times final velocity of A plus mass B times final velocity of what? B. This is the general equation. Is that okay? For calculation when dealing with conservation of linear momentum. Now I'm going to ask a question. What if these two objects, after colliding, they stick together, form one single unit, and then move in the same direction? That is after collision, Something like this. This one moves in and then collide. And both of them stick together and move in one direction. Of course, they will have the same velocity, the same final velocity. Therefore, VA will be equal to VB. And we simply call it what? V subscript C. That VC there, we refer to it as their common velocity. Common final velocity, I hope I'm communicating. So, if this VA in that case is the same as VB, which we use VC for it, we can factorize this common velocity out and simply add the masses MA and MB. So you take note of this equation. 1A is obtained from equation 1 on the condition that after collision the objects stick together and move with the same velocity. Now, we want to look at a case where the objects initially move in opposite direction. So they are moving towards each other like this. You can see the diagram. You know that in this case now, momentum, one of them would carry negative value of momentum because the direction is opposite. So if we choose to say, okay, let object A be assigned a positive momentum, then object B will be assigned a negative momentum, since its direction will be opposite to that of what? A. And in that case, this part of the formula initially, when you add in this and this is where you're going to get the momentum of object B will be negative, so that you'll be getting plus times minus. Are you following? And eventually the formula becomes this. You can see similar to this, but the sign is minus due to the opposite movement. Until now, we've learned a lot about linear momentum impulse. Now we want to look at the types of collision. Alright? It's very important that we consider that, because we stated a law known as the law of conservation of momentum, which states that during the interaction of objects, or simply during collision of objects, total momentum of the system is conserved. But have you asked yourself a question about the kinetic energy? Is the kinetic energy also conserved? Well, it may not. The types of collision here will give us more information about that. The first we have here is explosive collision, or simply explosion. Alright? This collision is also known as one-to-many. Imagine one object colliding and then scattering. It happens in the case of fireworks. Alright, fireworks. So you might just wonder where it gets its energy from. Remember, it has a stored potential energy. If you fire a firework, if you project it, it reaches a maximum height and then it scatters. The knowledge of projectile helps us to calculate the maximum height at which it explodes. So, such type of collision is known as explosion. It is a one-to-many type of collision. In such a case, the kinetic energy of the object after collision will increase. Therefore means that the initial kinetic energy in explosion type of collision is less than the final kinetic energy. So in summary, we can say that an explosion type of collision is one in which the final kinetic energy increases. It's greater than the initial kinetic energy. Now let us quickly move on to another type. This is the first type, that is explosion. We want to consider inelastic collision. Inelastic collision is also a many to one type of collision. Many to what? One. It happens in the case where you have two or more objects interacting. But when they collide, they now stick. So it forms a single system, a unit. But you have more than one of these objects initially that collided. But after collision, they stick together to form a single unit. In such case, the kinetic energy after collision, that is the final kinetic energy, will decrease. It therefore means that inelastic collision, also known as many to one type of collision, is that in which the final kinetic energy is less than the initial kinetic energy. Then the other way around, it means that initial kinetic energy is greater than the final, even if the total momentum of the system is conserved. Let's move on to perfectly inelastic collision. Still a many to one type of collision, alright? It's still similar to this. The difference is that in the case of inelastic collision, the final kinetic energy is not zero. It will decrease, no argument, but it will not become zero. In the case of perfectly inelastic collision, the final kinetic energy decreases down to zero. Therefore, after collision, the object becomes motionless, So this is the condition, you want to take note of that. Both inelastic and perfectly inelastic collision, they are many to one. The difference is, inelastic collision, the final kinetic energy is not zero. But perfectly inelastic collision, the final kinetic energy is zero. And hence, the object becomes motionless after collision. Number 4 is elastic collision. This is a many to many type of collision. Imagine you have two or more objects colliding and then they move away from each other. Is that okay? So such type of collision is known as elastic collision. In the process, after collision, the initial and final kinetic energy are equal. So that's the condition for elastic collision. In the next video, we now set the questions to solve based on all we've learned on the linear momentum.